All right, so just a side note, I reviewed the exams over the weekend and added partial credits. So if you haven't already, go back in, check your exam score. Um, you know, I'd say at least half the class or more got at least a few points of partial credit added on. So take a look at your updated score. If you have any questions about the details of where the partial credit came from, just shoot me an email or pop in office hours, and I'm happy to show you that. There's a text box on my end that I can put notes into. I don't think you can see it on your end though, but I always put notes in for exactly what problems I added partial credit for and exactly how much partial credit I added for each problem. So if you ever have a question, um, what you got credit for, whatever, I can super easily just copy that information and send it along to you if you're interested. The plan today is to continue on with polynomials. So we're going through chapter 6 where we're looking at algebraic properties related to polynomials. We're looking at, in some sense, kind of expanding the complexity of polynomials. In chapter 7, we're going to work on going in the opposite direction. We're going to work on factoring. And factoring is a topic that students often kind of struggle with. And I think part of the reason that students struggle with factoring is that it builds off of this chapter 6 material. So if you don't have a super good grasp of the chapter 6 material, that makes the chapter 7 material, where we're kind of going the opposite direction of chapter 6, that much more difficult. So we do have spring break coming up next week. So what I would recommend is, not just kind of getting completely away from the material for what would amount to about a whole week and a half, but maybe over spring break, maybe 2 or 3 times, just touch base with the material, spend an hour or two, a couple times throughout that week. I know it, feels like you just want to de-stress or whatever, but spend an hour, maybe 2 hours, say 2 or 3 times throughout that week, and just go back through some of this material. Just drill a few problems from each of these sections in chapter 6, go back through, just do 10 or 15 problems a few times, and that'll kind of keep you up to speed. When we come back and get into chapter 7, that will hopefully have solidified these chapter 6 concepts and prepared you well for chapter 7 and factoring. The quote of the day today is attributed to Albert Einstein. I'm always, for somebody like Einstein, somebody who's very popular and, seen as like a sage, it's always a little dangerous to take a quote that's attributed to him and just presume that he actually said it. So because people will often attribute quotes that other people have said to somebody more famous to, make themselves a little more credible. So this is attributed to Einstein. I'm not 100% sure if he said it or wrote it, but sounds like something he could have said. Everything should be made as simple as possible, but no simpler. And in mathematics, we're quite often interested in modeling real world phenomena. So we need to come up with mathematical models. And these models are always simplifications of the real world, because understanding models should be easier to understand than the full complexities of the real world. That's why we work with models. But if we make them too simple, if we make our models too simple and ignore too many aspects of the physical reality, we lose the ability to make good predictions with our model. So there is a nice medium in there. And also, if we can do if we can have the same predictive efficiency or efficacy with a simpler model as with a more complex model, it's probably better to use the simpler model. Practically speaking, where does this maybe apply to math? So that's a little more abstract, but we always want to reduce complexity before increasing it. So for instance, when we were going through our equation solving strategy, at every step, we would combine like terms, we would simplify fractions, we would, right? At every step, we want our complexity over time to look like this. So here is time and here's complexity, right? We do one step, we add a term to both sides. Now we have more terms floating around. And then we combine like terms and simplify, we decrease the complexity back down before we go into the next step. Now, sometimes we can, when we get used to a problem, we can get away with something like this. We can maybe add a couple of terms to both sides to get all of the variables on one side and all of the constants on the other side all in one step. If we can handle a little more complexity, and then we can simplify on the other side, and sometimes that's okay, but we probably don't want to do something like this, make the problem really big and complex, and then try to work our way down the other side. That's going to be more a lot more challenging. I think also in general, both in math and in life, difficulty scales non-linearly with complexity. And what I mean by that is, if we were to look at a graph of complexity versus difficulty, how hard is something versus how complicated is it? It's not just a straight line, right? If we make something twice as complex or as complicated, it's a lot more than twice as difficult for us to deal with. So kind of a practical example, my wife and her family lived in Northern Ireland for the last 5-ish years. And they recently, just this past summer, came back to the US. So they're here. It's super exciting. I get to hang out with my nieces all the time, but that was a huge complex operation, right? Moving countries, you have the girls in school, they got to find a school, the adults have to find jobs, they have to find a place to live. There's enormous amount of complexity already. So you need to take everything else that you can and make it as simple as possible, right? Because if you add complexity onto complexity, it's going to become insurmountable. So I think this idea applies to life as well as, math and modeling and these technical fields. Okay, and we're going to keep that in mind as we go through here. When we perform a step, we're going to try to remember, bring it back to first principles. We're going to try to remember the foundational principles we're applying. We're going to try to simplify everything after each step. All right, so what is the plan for today? Specifically multiplying polynomials, and then a little bit on special products. Special products is really just a special case of the more general idea of multiplying polynomials. So what I have here is a couple of, or several different products that we want to multiply and simplify. I actually changed my mind. I want to cover this one second. Changing my mind on the fly. So one of my grad professors always said, never think within 5 feet of the board. In other words, have your lecture completely prepped and ready to go. So I just thought within 5 feet of my computer. So who knows, maybe that's a bad idea. But so we're going to work through these 4 just as kind of practice examples, and we're going to look at how we might apply the similar ideas to what we've seen already, and even as far back as chapter 2 or chapter 1, or even really in MAT090. How can we just apply those same foundational algebraic principles in slightly different contexts? So this first example I have up here, 3 times x plus 1. That's something that we've seen a bunch of times already, just throughout chapter 2, or again, even in maybe MAT080. We know this is just an application of the distributive property. We have one thing multiplied by a binomial. In this case, we could even give this first bit here, this 3, we could give it a name in terms of polynomials and so on. It actually is really just a monomial, right? I mean, it's just a number, but just the number by itself is kind of just a polynomial with one term. It's just like this plus 1 term here on the binomial. And here I have a binomial. It's a binomial because it has 2 terms. It has 2 pieces that are connected together with a plus or a minus. And my distributive property says that I can distribute a monomial through a binomial by taking the monomial times the first term of the binomial, and then in this case plus, or using whatever the same connector is here, plus or minus, that same monomial times the second term of the binomial. And what does this get us? This gets us 3 times x is just 3x. 3 times 1 is 3. So we didn't really learn anything new here. Right, 3 times x plus 1 equals 3x plus 3. We've done that 1,000 times. But what we really did was we shifted slightly the way that we're thinking about this. We're thinking of that thing in front that's being distributed into the parentheses. We're thinking of that as a monomial, as a single piece that's moving along. And we're thinking about the thing in parentheses as a binomial, as something that has 2 terms connected with a plus or a minus. So the distributive property says we can distribute monomials into binomials this way. Now, something that we haven't seen too often before is the same idea, but written slightly differently. Here I have a binomial first, times a monomial second. Now, something to remember is that multiplication is commutative, so I could write parentheses x plus 1 and parentheses times x. If I really wanted to, I could just flip-flop that and write that as x times parentheses x plus 1. So there's not much difference between this question and the question above. My distributive property works the other way as well. My distributive property can actually go either direction. I can distribute the right factor into the left binomial, or a left factor into a right binomial. So our distributive property is both left distributive and right distributive. There are some other distributive properties, like say that relate to powers or exponents. Some of those properties that we might call a distributive property are, say, only distributive in one direction, but not the other. But in this case, it doesn't really matter. So we can use our distributive property the other way, and we get the first term of the binomial times the monomial. Our connector is plus. The second term of the binomial times our monomial. And here we get x times x is x squared, plus 1 times x is just plus x. Okay, so what if I were to look at something like the third example here, 3x times x plus 1? If I really wanted to force the issue, I suppose I could do something like, say this is 3 times x plus 1, like maybe distribute the x into the x plus 1. So I could maybe do something like this. Distribute the x in. That would give me a binomial, and then I could take 3 times that binomial and distribute the 3. That seems like an awful lot of work. Can I really lean on the generalization I made up here that monomials in general distribute into binomials? So I could really think of, let me get myself a space here. I could really think of this 3x as like being a whole monomial. It acts just like a 3 would, or just like an x would. So again, I have a monomial multiplied by a binomial. I can distribute the monomial into the binomial by multiplying by each term. So 3x my monomial times the first term of the binomial x, plus, because I have a plus connecting them, 3x my monomial times the second term of my binomial 1. Or this is 3x squared. The x times x makes an x squared plus 3x. And then lastly, for this kind of shift in perspective, I have what I can think of, I have 3x times x squared plus x plus 1, and I can think of this as a monomial times what we might call a trinomial, or more generally, just a polynomial. I have a monomial multiplied by a 3-term polynomial. There are 3 components that are connected by pluses or minuses. Now, addition's associative. So again, if I really wanted to force the issue, I could say group together those first 2 terms inside the parentheses. Now I have nested parentheses. I now have a binomial. I have a parentheses term plus 1. There are now 2 things connected together by plus. I could distribute the 3x into here by multiplying by the x squared plus x, and then by multiplying by the 1. So I would get something like 3x times x squared plus x plus 3x times 1. And then I could take a monomial again and distribute into this binomial. So if I really wanted to force the issue and only use the distributive property as monomials distributing into binomials specifically, I can kind of hack the problem to work this way. But that added a bunch of intermediate work. But I realized that in effect, all that I did was distribute the 3x to each term in the polynomial. And really, that's kind of our more general, that's our more general distributive property. Is if I have a monomial multiplied by a polynomial, if I have a single term multiplied by, in parentheses, a bunch of terms added or subtracted together, then to distribute, I just multiply that monomial out in front by each of the terms inside the parentheses. So instead of going through this whole, associative property and making nested parentheses and all of that, I'm just going to say, okay, I need to distribute the 3x to the x squared term, to the x term, and to that last constant term of 1. I have a plus here because my x squared and x are connected with a plus. I have a plus here because x and 1, x plus 1, they're connected with a plus. X times x squared, that's x to the first times x squared. That's the same base. I add the powers. First power plus second power is third power. X times x is x squared. And then 3x times 1 is just 3x. Okay, so just to recap, what have I done in these couple problems? Well, the first thing I did was take a problem that I'm very familiar with and just kind of rephrase it or rethink about it in terms of binomials and monomials. We looked at an example that maybe we're a little less familiar with seeing, and we realized that that's really the same problem as the first example. We can distribute kind of left into right or right into left. Either way is fine. We looked at a more general example where now we have a monomial, a true monomial, something like 3x, not kind of a boring one that's just a constant or something, multiplied by a binomial. What does that look like? We can distribute that whole monomial both factors through the two terms of the binomial. And then lastly, what if we had, instead of just the binomial, a polynomial, we can follow that same pattern. The same pattern as the binomial, where the monomial in front gets multiplied by each term, and we connect those terms with the same connector that we see inside of the binomial. That same pattern does extend to polynomials. If we have for instance, a 3-term polynomial here that's quadratic, or even if we had a 4 or 5 or 6-term polynomial, we just do the same process. A lot of math is pattern recognition. So I look at this problem, which I'm having trouble selecting. There we go. I look at this problem. I see how to solve that on the basis of following the pattern that I saw from this problem. I look at this problem and I understand how to solve it on the basis of the pattern that I see from that problem, right? So a lot of this pattern recognition, or this generalization through abstraction, we say, okay, I mean, I know how to multiply monomial by a binomial, but what does that pattern look like on the right side? And then will that pattern hold more generally? And we did show carefully that it does hold more generally. That was those scribbles down below. But I don't want to do that on every problem. I just did that to kind of convince myself that, okay, yeah, this pattern does actually hold more generally. Sometimes we think we see a pattern and it turns out that it doesn't really hold in the general case, but in this case it does. So now that we know that pattern holds, we can use this general idea of the distributive property, that if we're distributing one thing into the sum or difference of multiple things, we just multiply the outside thing by the first term, the outside thing by the second term, by the third term, and so on. And then we add or subtract the same way that was added or subtracted inside of the thing we're distributing into. Okay, so let's work through some examples here. So here's one that's that could be a bit challenging if we're not careful. I have negative z squared times 3z squared minus 2zy plus 1. A couple of different things going on here. One is that we have, in our monomial in front, we have a power, we have a negative sign. We'll have to think about that a little bit. The other thing is we have more than one variable. All the ones up here just use the single variable x as we were kind of warming up. But here I have a z and I have y. Okay, does having different variables, say 2 variables in this case, does that change the algebraic properties? Does that change how things multiply or how things distribute or how things add? Well, no, it doesn't. It does affect what we might call like terms versus unlike terms. It affects that. But it doesn't affect these fundamental properties. So let me come in here. I'm going to, again, give myself a little bit of extra space because otherwise I'll just make a mess out of it. I'm going to cordon off this whole first monomial here. So this whole negative z squared, that's a single term. It's the only term that's in that polynomial, so it's a monomial. I'm distributing it into a polynomial with 3 terms. This monomial is second degree, and the polynomial is also second degree because the highest power that we see is 2. And this zy kind of has 1 power plus 1 power, or 2 powers as well. So again, if I want to distribute a monomial into a polynomial, what's the pattern? Well, I take the monomial, multiply it by the first term of the polynomial, by the second, by the third term, and then I connect them with the respective plus or minus signs. So my monomial is negative z squared. that gets multiplied by 3z squared. Then minus, because of this minus sign, my monomial is negative z squared. It gets multiplied by the second term, 2zy, and then plus, because of this plus, my monomial multiplied by my third term. At this point, I've done the hardest part, the distributive property. I've been very careful with my pluses and minuses. I didn't drop any negatives. If I do this too quickly, it can be really easy to drop the negative attached to the z squared, or to forget that this connector here was a minus and not a plus and throw a plus in there by accident. So I just want to take my time. If it takes me one extra step to do, if it takes me an extra 15 seconds to write out, that's a pretty good cost benefit ratio. If it takes 15 seconds to, not mess up the problem versus doing it 15 seconds faster and having a higher chance of making an error. Okay, so now for this first term here, I have two monomials multiplied together. I have a -1 times a 3. That's just a -3. Z squared times z squared, that's the same base. So I add the exponents, same base multiplied together, add the exponents. That's z to the power 4, z to the power 2 plus 2. For my next term, I have minus a -2 for the constant. Well, that's going to be a plus 2. I have z squared times z. Well, that's, again, multiplied together, same base. I add the exponents. That's z to the 2 plus, remember, z, we think of as just z to the first power. So the exponents are 2 plus 1, or z cubed, times y. There's no other y, so we don't have any other any change to the power or anything like that. That y just kind of comes along for the ride. And again, remember, this plus comes from minus the negative, so those two negatives cancel out and give me a plus. And then here I have plus a negative z squared times 1. Well, that's just minus z squared. At this point, I would want to ask myself, do I have any like terms? Is there any simplification that I can do? And the answer is no. I don't have any terms. I mean, I see, just looking at the z's, I have a fourth, a third, and a second power. I would have to have the same variables as the same powers, but that's clearly not going to work here. Okay. Okay, so let's do a practice problem on that. We'll just take about maybe 90 seconds or so for this one. Let me zoom this in a little so it's a little bigger on your screen. We'll take about 90 seconds for this one, but this is a pretty similar one to the one we just did. Take about 90 seconds, work through it, and then we'll come back and discuss it. Okay, let's look at this problem. So here we have, again, a monomial times a polynomial, 3 terms. So we're going to distribute 3 times. And I go a little faster on this one than I did on the one in the example. Negative 2y squared times 6y squared plus negative 2y squared times 3y minus negative 2y squared times 1. In my first term, I can multiply all the constants together first. Negative 2 times 6 is negative 12. Y squared times y squared, same base. I add the powers, y to the 2 plus 2, or 4th power. In my second term, again, I multiply the constants. I get negative 2 times 3 is negative 6. The plus doesn't change that sign. Sorry, negative 6, the plus does not change that sign. So we get a minus 6. And then y squared times y. So we have a product of 2 factors, same base. We add the powers, y to the 3rd power. And now we have minus times minus 2y squared. That's a plus 2y squared. I look through, I see that I have a bunch of the same variable, but it's always to a different power in a different term. So no like terms, there's no more simplification I can do. That's as simple as I can make it. Okay, so now let's really move into really the kind of crux of this this section, really the next 2 sections. We really want to move into where we're multiplying polynomials by polynomials, not just monomial by a polynomial. So I need to understand how to handle something like this. Something where I have a binomial multiplied by a binomial, and we're working up to more generally something like polynomial times polynomial. And you might kind of have vague memories of, say, the FOIL method or something like that, but we're going to kind of take this from first principles. So the x plus 1 is a binomial, the x plus 2 is a binomial, they're multiplied together. But I'm a little stuck because I have a way of multiplying a monomial. Oops, my things got misaligned there. I have a way of multiplying a monomial into a polynomial, or distributing a monomial into a polynomial. But I'm not exactly sure how to distribute a binomial into a binomial directly. But I can kind of, maybe cheat a little bit here. And I can say, well, what if I took this first one? And what if I kind of thought about it as a monomial? And what do I mean by that? I mean, and so when I look at the second factor, I'm looking kind of inside the parentheses and seeing that there are 2 terms inside the parentheses. But what if I look at this first factor just as a single thing? Parentheses x plus 1 and parentheses, if I just view that, if I kind of zoom out or blur my vision a little bit, and I view that parentheses x plus 1 and parentheses as just one thing. I mean, if I really wanted to take it to the extreme, I could relabel, say, y equals x plus 1, and then I just have y times x plus 2, and then I really do have a monomial. But if I just think of this first parentheses as a whole, parentheses x plus 1 and parentheses, I can treat that like a monomial, distribute it into the binomial. Maybe that'll get me somewhere. What would I have then? I would have my quote monomial, my kind of pretend monomial, times the first term in the binomial. My connector is a plus. And then my pretend monomial times the second term in the binomial. Now this didn't get me the final answer, but it did get me something that's a little bit more, a little bit easier to deal with. It's a little bit more complicated. It's a little more complex. There's more stuff going on, but the stuff that's going on is easier for me to handle because now what do I have? Now I truly do have monomial times binomial, and I can distribute this way. And I truly do have monomial times binomial, and I can distribute here. I've taken a big problem and I've split it into two problems, each of which are simpler. This is what a lot of the kind of practical side of doing mathematics looks like, is taking a big problem, splitting it into two problems that are a little bit simpler, maybe splitting each of those into two problems that are a little simpler still, and getting down to the point where you have solved basically a whole bunch of trivial problems. So I broke binomial times binomial by kind of pretending that one of them was a monomial and distributing that whole parenthesis x plus 1. I broke that into two cases of monomial times binomial, and I know how to solve that. I've reduced my new problem to a previously solved problem. That's another, very common idea in mathematics. If I know how to solve a problem that's a little simpler, and I have a problem that I am not sure how to solve, can I make the problem I'm not sure how to solve look like a problem that I already know how to solve? And then once I kind of make that connection, then the solution proceeds pretty easily from there because I know how to solve that problem. If I can reduce a problem to a previously solved problem, that's always a big plus. So again, what am I going to do in each of these two terms connected by this plus? I'm going to do a distributive property. In this case, distributing the x into the x plus 1. So I have the first term of the binomial x times the monomial x. My connector is a plus. The second term of the binomial is a 1 times the monomial x. So this all came from here. My connector plus can just come down. If my connector was a minus, I'd have to be very careful to distribute that minus as well. But in this case, the plus, it just comes down. And then I do a similar thing, distributing the monomial into the binomial. First term in the binomial, x times monomial 2. My connector is a plus. Oh, I covered up my 1 there. And then second term of the binomial, 1 multiplied by the monomial 2. So that x plus 1 all times 2 split into these two terms. So now, things almost look a lot worse than they did before because now I've got a whole bunch of terms. But each term has just a really simple operation to do. I just have to multiply two monomials together. X times x is x squared. 1 times x is just x. Plus 2 times x plus 2. Right? Or if I write this a little cleaner, this is what I end up with. And then the last thing I want to do is I want to check and see, can I simplify any further? Are there any like terms I can combine? Well, x squared doesn't combine with anything. The 2 doesn't combine with anything, but this x and the 2x, they are like terms. They have the same variable x to the same power, first power. They can combine together by adding their coefficients. So the x term here is really just a 1 times x. So the coefficient 1 plus 2 gives me a 3. So when I'm expanding out like this, when I'm multiplying out, in a sense, it kind of, it makes the problem look worse and worse for a little while, because I end up with more and more stuff that I'm writing down. But really what I'm doing is I'm splitting the problem apart into a bunch of tiny problems, right? At the end here, I had to do 4 calculations, but each one of them was quite simple. At least it's quite simple relative to the complexity of what we started with, multiplying a binomial by a binomial. So let's look at this example then. Y plus 2 times 3y minus 4. Does it matter that the variable is y instead of x? No, doesn't make a difference. The algebra, the properties, and all of that are still the same. I'm going to do my same approach. I'm going to treat this first one as if it were a monomial. So I'm going to treat y plus 2 in parentheses all as kind of one thing. When I move it around, I'm going to move it around as a whole. It's always going to stay as parentheses, y plus 2 and parentheses. And then for that second bit, for that binomial, 3y minus 4, I'm going to think of that as 2 terms, the 3y term and the 4 term that are connected by a minus sign. So I'm going to distribute this whole monomial, so to speak, into the 3y and then into the 4. So what do I get? I get my quote monomial, my pretend monomial, y plus 2, multiplied by the first term of the binomial. My connector is a minus. I get my, again, kind of pretend monomial, y plus 2, times the second term in the binomial, 4. Yeah, is there a question? Okay. All right. So we've distributed our first bit here, this y plus 2, that we're kind of treating like a monomial. We're treating it as one thing, parentheses, y plus 2 and parentheses. We distributed that into both terms of the binomial, the 3y and the 4 term, and connected them with a minus. And again, now we have truly a monomial times a binomial times a binomial. We now have 2 instances of distributing a monomial into a binomial. We know how to do that already. So 3y distributes into y plus 2. Y times 3y, connector is a plus 2 times 3y. Okay, that's not too bad. I do have a little bit of a complication here, though. I have minus all of this stuff, which is parentheses y plus 2 and parentheses times 4. Now, what if I'm going to cross my fingers and hope that this will copy correctly. I'm going to come over here. Oh. I think somebody might have their microphone on. Is there Oh, okay.
Yeah, that was rude. Sorry.
Oh, no, you're good. Did you have a question, or if anybody has a question? Uh, yeah, if anybody has a question, just feel free to stop me. Um, but let's say we had something, um, I don't know, I'm not going to write all of this stuff, but let's just say it was 3 minus parentheses y plus 2 in parentheses times 4. Well, what if instead of having the 4 at the end, what if we had it at the beginning? Like this. I'm having trouble getting my cursor to cooperate. There we go. Well, we've seen problems like this before. How did we deal with this? Well, we said this was 3 plus -4 times y plus 2. So we made it a plus a -4. And then we distributed the -4. And I'll do it in a couple steps. But the main thing that I see is that my negative gets distributed along with the 4. It's super easy to miss that second negative. So this was just scratch work on the side. This wasn't really necessarily solving this problem. So, but just to remember that we had to be really careful when we had a situation like this. Same thing over here. So in this case, I could do something like, make this whatever plus a -1 times y plus 2 times 4. That seems a bit overly complicated. What I would probably recommend is before approaching a problem like this, let's kind of set ourselves up a little better for success. I know that multiplication is commutative, so this 4 can pop out front. Y plus 2 times 4 is the same as 4 times y plus 2. The order that we multiply in doesn't matter. And if I do that, this looks a little more familiar. Let me just copy all of this down. But because I know that distributing negatives, I kind of, that sets off an alarm bell in my head, and I say, I know that it's super easy to mess this up. I'm going to be extra careful. I, again, put my 4 in front. This -4, or this -4 becomes a plus -4. I know that that's a good way to distribute in this case. And now I distribute this -4 monomial to the y into the 2. Again, really easy to be, to go just a little bit too quickly and forget one of these minus signs on one of these terms. And I'm not doing anything with these first couple of terms because I really want to focus on these, on the operations that I'm doing on the right side here. All right, so then I have plus -4 times y, and then plus -4 times 2. So I know that I kind of did a little extra work here. Maybe I could have gotten away with not writing out these 2 lines, but maybe I would have not written out those 2 lines, dropped the minus sign, and got the wrong answer. So when I see that I have a negative that has to get distributed, I just want to be extra careful, write out an extra line, maybe an extra 2 lines, and make sure that I get it right. But now I have all my terms split apart. I want to go through and simplify everything. So y times 3y is 3y squared, plus 2 times 3y is 6y, plus a negative 4 times y, that's minus 4y, and then plus negative 4 times 2 is minus 8. Or this is 3y squared. That doesn't have any other like terms. There are no other y squareds. The plus 6y and the minus 4y, they are like terms. They have the same variable y to the same power 1. So I add or subtract the coefficients. Plus 6 minus 4 is plus 2y. And then minus 8, there are no other constant terms anywhere, so that's the simplified answer. Okay, so we've now seen two examples of multiplying a binomial times binomial. I'm going to come over here. And here we've used the distributive property. We could also use kind of a vertical multiplication property. Personally, or vertical multiplication method. Personally, I like just using the distributive property. I think that's kind of the way to go. As far as applying a property that's a little more direct. The vertical multiplication method to me always seems like a bit unnecessary, but I would like to go through it just to show it one time in an example, mainly because I think it gives a little bit of clarity into why the vertical multiplication works in arithmetic when we're multiplying, say, two-digit numbers, something like that. And it's, I think, maybe a little bit helpful to see what's going on. It kind of connects some of those arithmetic concepts to some of these algebraic concepts. So let's again take a look, and let's see if I can select it. Let's take a look at this same problem, but we're going to approach it a little bit differently. If I had, something like 13 times 11, I could think of this as like 10 plus 3 times 10 plus 1. Right? I could split it up this way into my tens bits and my units bits. Or if I had something like, like 23 times 11, I might choose to write that as 2 times 10 plus 3, and maybe 11 would still be 10 plus 1. If I wanted to multiply out 23 times 11, I'd come over here, I'd do this. I would multiply this units digit, digits place 1, or units place 1, by the 3 and by the 2. And then I'd multiply the tens place 1 by the 3. I'd write that under here. And by the 2, I would add down. And that's what I would get, right? We learned this algorithm, this process for solving this type of a problem, but I think a lot of times we don't really understand where it really comes from. Like, why is this shifted over 1? Some of these kind of questions. So what we're going to do is we're going to approach solving this multiplication of two binomials in a similar way. We're going to say I have an x plus 1 times x plus 2. I'm going to do something similar. I'm going to take my constant term on the bottom, multiply it by the constant term and then the x term on the top. 2 times 1 is 2. 2 times x is 2x. Those are connected with a plus. Then I'm going to take my x term on the bottom, multiply it by the 1, and then by the x. I'm going to do just like I did in the arithmetic multiplication. I'm going to shift over one place. X times 1 is x. Now we see why I did that, because now the x terms line up. X times x is x squared. Those come together with a plus, and then I add down. So again, if I thought of like 23 times 11 as 2 times 10 plus 3 times 10 plus 1, that's kind of like 2 times x plus 3 times x plus 1 if we were to just choose x equals 10. So we could see how these multiplication algorithms are similar between the arithmetic example and this more algebraic example. And we really see that what we're doing is we're grouping together, in this case, the like terms. We have one column for the constants. We have one column for the x to the first powers, one column for the x to the second powers. In something like 23 times 11, I had the number 1 times the number 3 was just 3. The number 1 was multiplied by this 2, but that 2 is kind of a 20, right? It's like a 2 times 10. So 1 times 2 times 10 gets 1 factor of 10 on it. And similarly down here, I have this 1 this 1 is in the tens place. It's kind of like a 10. So 10 times 3, 1 times 10 times 3 gives me 3 times, again, 1 factor of 10.
I have a question.
Just a second. And then
Okay.
so just let me finish up this piece here. And then lastly, we have 1 times 10 multiplied by 2 times 10. This column has 2 factors of 10. So we have 1 times 2 is 2. We have 1 factor of 10 coming from here, another factor of 10 coming from there, 2 factors of 10 for this column. So hopefully this gives us a little bit of insight into how that arithmetic or arithmetic multiplication works. Yeah, so question.
Yes.
Mhm.
I wanted to know, like, okay, y can equal 1, right? Can x equal 1?
Um,
Like if you was using in an equation.
you mean like if we had this expression, could we substitute in 1 for x?
Yes.
Yeah, definitely. Yeah. So any of our variables, most of the time that we list a variable, we can really substitute any real number in for that variable. There can be cases like later on later on in the course, you might see something like 1 over x. Well, then like x can't be 0 because otherwise we'd be dividing by 0. But kind of as a typical rule, anytime that we see a variable, we can substitute in any number we want into that variable if we wanted to. Yeah. Yeah. So
Thank you.
yeah, definitely. Yes. So hopefully this kind of makes a little more sense how this binomial multiplication corresponds to the arithmetic multiplication. But again, personally, I wouldn't use this as an actual method to multiply binomials. I think it's a little cumbersome and a little lengthy to write out, and perhaps maybe a little bit error prone. If you use the distributive property, I think it's much easier to deal with things that come up like subtractions that you have to distribute and things like that. Um, and then we'll also learn up next is the so-called FOIL method. So FOIL method is great after you've done several problems and you're kind of used to all of the different things that can pop up that are a little challenging, and you're comfortable with the distributive property. Once you're good with that, the FOIL method is kind of a shortcut method. So we'll learn the FOIL method in a couple minutes here, but the FOIL method has two drawbacks. One, it only applies to a certain case, and two, again, if you're not super comfortable with the distributive property, the FOIL method is a shortcut method. So when some of these strange things come up, like having to deal with minus signs and things like that, and if you use the FOIL method too early, or not carefully enough, it can sometimes lead you in the wrong direction. But before we get to the FOIL method, let's go through two examples. So work through these two using the distributive method. We'll take maybe 4 minutes for these. And again, both of these have a minus sign in them. So just be super careful with that. So we'll take something like 4 or 5 minutes, work through these two, and then we'll come back and discuss them. Okay, so hopefully you were able to uh, get these two answers. Again, if you, as always, if you didn't quite finish the second problem in time, that's not a big deal. I know we're just learning this, you can make a mistake and then go back or something. So it's not, if you didn't quite get it as fast as I did, that's not a problem. But for our first one, again, we start with distributing the first binomial, kind of treating it as a whole, kind of pretending that it's a monomial, distributing it into 2y plus 1. So we get y minus 3 times 2y plus y minus 3 times 1. And I think this is a pretty straightforward process. We just then distribute the 2y into the y minus 3, distribute the 1 into the y minus 3. We take each of our terms and we simplify. We get a 2y squared minus 3 times 2y, or minus 6y, plus y minus 3. And then we look through and we see, okay, the minus 6y term and the plus y term, those are like terms. They can be combined together. They both have the same variable y to the same power 1. So we add the coefficients. Negative 6 plus 5, or negative 6 plus 1 is negative 5. The other two terms don't have any other like terms, so they just come down as themselves, and that's our answer. For the next one, we have to be a little careful for a couple reasons. One is, well, this is a little unusual. We had a 2z squared here instead of just the variable to the first power. So one of our binomials is a first degree, a linear, but one of our binomials is a second degree. So that's a little interesting. The other thing that I have to be careful of is when I do my first distributive property, I end up with this minus connecting these two big pieces. And again, I know that I recognize that this is a situation where it's very prone to error if I move too quickly, if I'm just not really careful. So I'm going to say, okay, I'm going to slow down here. I recognize this is kind of like almost like a dangerous situation, right? It's almost like if you're driving down the road and you see a bunch of kids walking on the sidewalk near the road or something, you're kind of paying extra close attention, right? I'm doing that here. So I say, what can I do to make my life a little easier so that I don't forget to distribute this negative properly? Maybe what I'll do is I'll take this 2. I have parentheses times 2. I can use the commutative property of multiplication, put that 2 in front. Then I have minus 2 times stuff. I'll just make that a plus and negative 2. Now the minus is kind of attached to my monomial, so to speak, right? Now I'm much less likely to forget to distribute it. This is by far my favorite way of dealing with these minuses, is make it a plus, parentheses, negative number, and it's so much easier to deal with then. So much less likely to forget to distribute that negative, because it just comes along with the 2, right? It comes along with the 2 here, and this second one is the one that's super easy to forget if you don't take extra care. And again, I go through, I simplify each of my terms. And in this case, I have the same variable everywhere, z, but I have a first power, a second power, a third power, and a constant. There are no like terms here. There's nothing more for me to combine. That was because I had this second degree times the first degree. When we have that, it turns out that we don't end up with any like terms. So we can just leave our resulting polynomial like this. If we wanted to, sometimes it's nice to write the terms in descending powers. So if we really wanted to be pedantic, whoops, I need a minus there. I might flip-flop these two just so that I have descending powers, but that would really just be kind of a taste or a style thing. If we write the polynomial in any form it's correct, we quite often want to write the highest power term first. that's just kind of an indication to us when we glance at it. If we're looking at, say, solving an equation or something, I know, oh, okay, this is a quadratic equation instead of a linear. It's just maybe a little easier to pick out. And then, so that's kind of, a little bit more standard. And then, writing the terms in decreasing powers. Again, maybe more of a taste thing. People usually write it this way, though. But if you were on an exam or something like that, I want to take the time to rearrange the terms. Okay, so now let's come back up to this problem that we've already solved two different ways, and we'll solve it one more time. So I'm going to come over here, and I'm going to kind of cordon off a little area for me to work in. I've already got a bunch of scratch work over here. And here we're going to talk about the FOIL method. So FOIL stands for first, outer or outside, inner or inside, and last. So what does this mean? Well, I have a binomial times a binomial. I have two terms times two terms. So that's the first important thing. This is for binomial times binomial. So each term, or sorry, each factor has two terms, a first and a last. So first, what that says is multiply my first terms together. Multiply first term in the first binomial times the first term in the second binomial. So that's x times x. Outer, I can think of there being inner and outer terms in each of the binomials. The inner terms are like the +1 in the first binomial and the x in the second binomial. Those are on the inside. And then outer as being the x in the first binomial and the +2 in the second. So this is my first. Outer, multiply the x by the 2. And I'm running out of space, so let me get rid of that. Inner, multiply the 1 by the x. So this is inner. And then last, I multiply the two last terms. The last term in the left binomial, the last term in the right binomial. So I get a 1 times 2. And you might realize that except for the swapping of the order, I suppose, of these middle two terms, we get exactly the same four terms that we got up here, except we didn't have to do this distributive step. We saved ourselves a step. And I can, of course, come down now and do x squared plus 2x plus x plus 2, x squared plus 3x plus 2. So I got from my product of two binomials to these four terms, I got that in one step instead of two steps. I didn't have to distribute, then do two more distributive properties. I just had to do my FOIL method, multiply the first, multiply the outside terms, the inside terms, and the last terms. So again, this is a nice little shortcut. It can save some time. But also, again, we have to be a little careful. Let's look at an example like this. and see where we could make a mistake. So if I do FOIL again, first, outside, inside, last, if I multiply my firsts, y times 3y, if I multiply my outside, I've got to be really careful here, because if I just did something like plus y times 4, is that the correct term? I got my y times 3y, that looks good, but my y times 4 term, well, that should be like a y times -4. I have to be super careful with my minuses. I have to really think of this 3y minus 4 really more as like a 3y plus -4, almost like that. So again, if I'm not used to working with these, if I haven't done several problems with the distributive property, if I haven't gotten used to being very careful with these negative signs and these minus signs, it can be easy to mess this up. So we see really I need to think about this as my outside being something like y times -4. And now that term does look the same as over here. My inside is 2 times 3y. And then last, again, being super careful with that negative that was attached to the 4, thinking of that -4 as a plus and -4. 2 times -4. And I can go on from here. So FOIL is nice in the sense that we get to skip this step. We don't have to, instead of doing 3 distributive properties, doing 1 from the to move to this second expression here, and then 2 more doing a distributive property here as well as there to move to the next line. Instead of doing this extra step and 3 distributive properties, I can just jump right to this line. But the downside is that, well, downsides, 2 of them, is 1, I have to be very careful when I have minuses or negatives, anything like that, to handle that appropriately. And if I'm not super used to taking care with those negative signs or minus signs, that's an easy place to trip up in the FOIL method. The second thing is when we look down below, which we're going to skip down to this example next. Here I have a binomial times a polynomial with 3 terms. I can kind of rig up a way to use the FOIL method here, but it's a bit of a pain, right? I could kind of think of maybe 3x squared plus 5x minus 2 as being 3x squared plus this term. If I just call this whole term, whole 5x minus 2, one term, then I can do like, firsts times outsides, where the 2x multiplies the whole 5x minus 2. I mean, we could maybe force the issue, but I think we could agree that the FOIL method is not going to work, at least not work super nicely, if we have anything besides binomial times binomial. So those are the shortcomings of the FOIL method. It, practically speaking, really is only good for binomial times binomial. And we have to be super careful with things like minus signs or negatives or anything like that. I had a couple extra problems here, just depending on how time went, that we could do or skip. We'll choose to skip those. And then we'll jump down to this example here. I don't think we'll quite get to special products today, but I do want to look at distributing a binomial into a polynomial with more than 2 terms. So again, we could use the vertical multiplication method. I think that's a bit cumbersome and not the easiest to use. We could use really force the issue and use the FOIL method. But again, that's really set up for binomial times binomial. This kind of leaves us with distributive property. But the nice thing is that the distributive property generalizes super nicely, right? If you have a choice of learning a method that only applies to a special case versus a method that applies very generally, I think the general method is the one to maybe lean on more heavily. The special case method might save you a little bit of time or effort in some scenarios, but I think going with the more general method is usually the advisable way to go. So let's think all the way back up here. When I wanted to multiply a monomial into a binomial, this is how I did it. If I wanted to multiply, there we go. If I wanted to multiply a monomial into a polynomial, the pattern was basically the same, right? The distributive property was basically the same, whether I was going into a binomial or a polynomial with more than two terms. Same idea here. And then remember the important idea of thinking of one of our binomials or polynomial terms, just kind of zooming out and thinking of one of them as a monomial, distributing that into the other binomial, or in this case, polynomial. So what's our strategy going to be here? We're going to distribute this whole 2x minus 1 into this polynomial. It's going to multiply the 3x squared, the 5x, and the negative 2. So there's distributing into the first term, plus, because that's our connector, there's the second term. And if you have a bunch of terms, sometimes it's nice to just literally check them off as you go along so you don't accidentally skip one, minus 2x minus 1 times 2, the third term, and I've gotten everything. So I had to do 3 multiplications here, one distributive property, and then I have to do 2 more in each of these distributive properties. So I'm going to do this a little more quickly. I'm distributing the 3x squared into 2x minus 1. Multiplying 3x squared times 2x gives me 3 times 2 is 6. X times x squared, that's a product of power functions where they have the same base, x. We add the powers, that's x to the third. 3x squared distributed into the minus 1 is a minus 3x squared. We have a plus 10x, 5x times 2x. That's going to be to the second power because we have x to the first times x to the first. The exponent is going to be 1 plus 1, or 2. And then plus minus 5x, that's a minus 5x. And then lastly, we remember, okay, this is the scenario where I can easily make a mistake. So I'm going to think of taking this 2. Oops, I missed the parentheses there, but that's okay. Putting it out in front and then sticking that minus sign onto the 2. So instead of a minus 2 times 2x minus 1, I have a plus negative 2 times 2x minus 1. And now when I distribute, that negative comes along much more naturally. So I get a minus 4x. Minus 2 times minus 1 is a plus 2. I see I have some like terms in the squares, the x squared terms, and in the x to the first terms. minus 3x squared plus 10x squared is plus 7x squared. Minus 5x minus 4x is minus 9x plus 2. And I have combined all of my like terms. All right, so let's go through one practice problem related to this. So if you want to work through this problem, we'll take maybe about 4 minutes to work through it, and I'll kind of, as usual, start about a minute in and start kind of working through it alongside you. And then we'll come back in about 4 minutes and just quickly wrap this up, and that'll take us about to the end of class. Okay, let's discuss this one. It was a little under 4 minutes, but I finished writing a little sooner, so I think it wasn't the whole 4 minutes. Again, as usual, if you didn't finish the whole problem, that's okay. But I really hope that you got through kind of the crux of the problem, which was the distributive properties, applying them kind of the one direction, then the other direction. So we distribute the x plus 1 into the 3 terms. X plus 1 times x squared plus x plus 1 times 2x plus x plus 1 times 2. And here we don't have any minus signs connecting anything. So this is actually a more straightforward problem. This next one would be a more challenging problem because we have minus signs everywhere in that one. We need to then distribute the x squared into the x plus 1, the 2x into the x plus 1, and the 2 into the x plus 1. And distributing and simplifying gives us x cubed plus x squared plus 2x squared plus 2x plus 2x, another 2x, plus 2. And then we identify like terms. We have two terms that have x squared in them, and we have two terms that have just x to the first power in them. So we have two sets of like terms. The x cubed doesn't have any other like terms, so it just comes down. X squared plus 2x squared. Again, same variable to same power. We add the coefficients. 1 plus 2 is 3x squared. 2x plus 2x is 4x, and then the plus 2 just comes down. Okay, I'll stop the recording.